Hello, ladies and gentlemen, it's Mr. Zabo coming at you with some 3D graphing, some 3D distance, and some reflections today. So we're going to start by 3D graphing. Excuse me, 3D graphing. And when we're talking about three-dimensional graphing, we're adding an additional axis. We've already traditionally had the X and Y axis. Now we're adding in the Z axis. Traditionally, when we're adding this third axis, we kind of rotate what all of the axes look like. So we have three axes. They are mutually perpendicular. So Z is perpendicular to X and to Y. Y is perpendicular to Z and X. X is perpendicular to Y and Z. And this is the traditional setup when we're showing this, where the X-axis is almost like it's popping out of your computer screen, out of the paper at you. Y-axis looks horizontal, Z-axis looks vertical, but that could be rotated in any different direction three-dimensionally. XY is how we would typically write a two-dimensional ordered pair. When we're dealing with three-dimensional graphing, we're looking at X, Y, Z. So the Z coordinate, our new coordinate, is always the third coordinate. You got to be real careful in plotting these ordered pairs so that when we're going 2, 3, 5, it's 2 in the X. Make sure you're identifying your X-axis. 3 in the Y, that's the Y-axis, and from there, 5 in this case in the Z direction. Next, we're going to talk about the distance formula. When we're talking about distance in 3 dimensions, it's pretty straightforward here, and you can kind of see it's pretty much the same thing, except we're now talking about the distance between our Z coordinates squared as well. So the distance between any points P and Q is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. That would be the two-dimensional distance. When we're adding the third dimension, we have to add z2 minus z1 squared. Press pause, take a minute and try number 1 at the bottom here. Remember, the origin in this case is at 0, 0, 0, using our distance formula. So hopefully we found that the distance between point P in this case and the origin is the square root of 38. Can't be simplified. We're going to leave it in that simplified radical form. Notice that I did 2 minus 0. I could have done 0 minus 2 and then 0 minus 3 and 0 minus 5. Sure, those would have been negatives, but when I square, negative 2 squared would still be positive 4. Negative 3 squared would still be positive 9, and negative 5 squared would still be positive 25. So no matter which way I did that subtraction, I'm still going to end up with the positive values here. So be very careful with your addition and your subtraction. Now we're going to start plotting some points and graphing some objects in 3 dimensions. Start with point D. It's at the origin. So I have my X coordinate sticking out, my Y coordinate, my Z coordinate. They're mutually perpendicular. 0, 0, 0 is still the origin of those three. I'm going to plot the point, label that as point D. Okay. When I'm plotting point A, my X coordinate is 4, so if I go from 0, I'm going 1, 2, 3, 4 units in the X direction, but 0 in the Y direction and 0 in the Z direction. So I'm using that entire diagonal there to plot point A. B, I'm going 4 in the X, 1, 2, 3 in the Y, but 0 in the Z, so I get my point B here. C, I go 0 in the X, just 3 in the Y, just to here, and 0 in the Z direction. That gets me point C. The height is 8. So what that's telling me is this is the bottom part of my rectangular prism. That's the base. And since it has a height of 8, that's telling me my Z coordinate. My Z coordinate is going to be 8 for all of my additional points. 1, 2, 3, 4, 5, 6, 7, 8 units up is going to get me my, I'll just call it D prime, but it's really just my next coordinate. C, I have an additional point 8 units up. B, I have 8 units up from B, so that's 1, 2, 3, 4, 5, 6, 7, 8 units up from B, and 8 units up from A, gets me my second base of this rectangular prism. Graphing in the height of 8 for all of those. And you can start to see that image of the rectangular prism. With that said, hopefully we're able to find and use some of our knowledge from previously to find the area and volume of that solid. Go ahead and press pause to try those. So the rectangle is the base in this case, and that's 3 times 4 because we've gone 4 units in the x direction, 3 units in the y direction at 12 square units, and then it has a height of 8. Area of the base times height is 96 units cubed. Finding the diagonal of the solid. At that point, what we're really looking to discover is you can pick any point on the top base and find the diagonal through the solid, remember. So if I'm going to choose, let's say, this point here, I want to find the distance to this point over here diagonally through the solid. If I would have picked this point here, I would have found the distance through the solid to point C. Okay, so any 2 points are going to have that same distance though. In my example, I chose 4 in the x, 3 in the y, and 8 in the z. 4, 3, 8. That's this ordered pair here with the origin. My second ordered pair would have been the origin, and I'm going to use the distance formula we discussed. Go ahead and press pause to try that. Maybe you use different coordinates, and that's perfectly fine. We should get the same answer. And in this case, we get the square root of 89. Part D should be easy. We just wrote that ordered pair, or that coordinate, I should say, down. 4, 3, 8 is this coordinate right up here, so yeah, absolutely, it's a vertex of this solid. Alright, so now we get to some pretty fun stuff, I think. We're going to start talking about reflections. And what we're looking at here is a mini golf hole. You know, all of us have probably seen, if not played, mini golf. We look at a ball down here, and we've got the hole up here. And we have to bank the ball in if we want to make a hole-in-one. So where do we aim? Is it just a guessing game? Well, mathematically, geometrically, we can find this using reflections. So to start with, what we're really looking at, if I call the hole point H, it is a very specific distance away from the wall that we're going to have to bounce our golf ball off of. And that distance is measured perpendicular. If I extend that and reflect over that wall, where this distance is identical to this distance, they're both perpendicular. Theoretically, I should be able to aim this ball directly at that hole back here. And it's hard to see that if we can try to draw that line in. Now, if I aim the trajectory along this line that would go right at that hole, I'm going to hit the wall at a point where it's going to bounce off directly into the hole for a hole-in-one. And this comes down a lot to the angles and the laws of physics. So there's a lot more that goes into this as far as the speed of the ball and whether you hit it with a spin and stuff like that. But if we take all of that out, if you hit it at the right speed, it's going to bounce right off this wall, and it's got an angle here, which is congruent to this angle here. Vertical angles are congruent. And it's going to bounce off at that same angle over here. Bouncing in and bouncing off. And I want to aim for that hole on the reflection point, and it's going to knock it straight into the hole. Now, what happens in this next example when there's something that's blocking that path? I can't hit the ball directly there and bounce it off once. Now I'm going to have to make multiple bounces, and so this line is not going to work for us. See if you can come up geometrically with a way that we can bounce the ball more than one time and still get a hole-in-one. Use the reflections and the angles of everything that we're dealing with here. Alright, so what I have here is the final route is that red one that I sketched over. You have to find not only an angle and use the reflection of the hole here, you also have to use a reflection of the ball. So if the ball was here, I'm going to have to reflect the ball over this wall, because I'm going to have to bank off that wall and then bank off that wall. Any wall that you have to bank off of, you need a reflection. So if I'm banking off of this wall, I need to find an equal distance where these are both perpendicular on the opposite side. Find that line that goes and connects the hole reflection with the ball reflection. And then the intersections here and here will provide the proper angles to make that bank shot. Alright, so there's going to be a few book problems that you guys are going to be able to practice, and we're going to do this again in our next session, where we're going to continue looking at reflections and bouncing things off, see how it's used in pool and in billiards, and just kind of get some practice with it that way next time we're together. Good luck, everybody. If you have questions, don't hesitate to let me know.